Hello everybody, welcome to cyberplace.org, the academic level online course platform for cybersecurity studies, the only website that is specially designed for university students majoring in computer science and engineering, as well as for high school students specializing in cybersecurity studies. The website presents 4 different learning subjects: network communication, cybersecurity programming in Python, operating systems, as well as network and web attacks, all in 5 different learning tracks: textbooks, video presentations, audio, multiple choice questions, and code challenges. I invite you to subscribe to this website, choose your preferred subject and learning track, and enjoy. Good luck. Welcome back to cyberplace.org. We're continuing our video presentations, and today with 2 very important subjects: addressing and routing, 2 very important functions of the IP, the third layer of the OSI model. Addressing is all about understanding if 2 machines are sharing the same subnetwork. When we assign an IP address, we may use several schemes, but at the end, the question is, do they share the same network in order for us to decide if we send the message directly between the source and destination or through the router to an external segment outside our local area network. Routing would be the next phase, deciding which NIC should we use in this router to forward it in the most efficient way to its target. We'll start with addressing and with the rather primitive approach called class-based addressing. Take a look at the following segments. Each portray a shared set of octets in its address framework. For example, in this segment, we see 3 octets which are shared across all its devices, 192.168.10, with different information stated only on its 4th octet, 0, 10, and 20. The same appears also here. While here we're seeing that the shared information is placed only on the left 2 octets, 172.16, while the right 2 octets differ, 00, 16, and 15. So the question is, what determines the shared information so that we know that machines reside within the same network? We can easily understand what our IP is, for example, using the IP command ipconfig or ifconfig in Unix. This ipconfig in Windows states 192.168.56.1. This information is obtained by our router. There are 3 schemes to provide a computer with an IP. Either it is fixed, provided by IANA, and stayed for the domain throughout its lifetime. This is the case with Google or with most, let's say, domains around. We don't want them to change because changing might lose traffic. The other 2 approaches are using a DHCP server, leasing an IP for several weeks or so by the DHCP server. This is again a real address, and the local router knows how to forward that message to us. The third option is getting a NAT address, a Martian address, with the form of 192.168 something something or 10.0 something something or 172.16 and so forth. This address is rather fake and it's temporary for the lifetime of the visit, meaning if we visit a network,
we are given an IP address temporarily until we leave it. And when we leave and return, we might get another address. The need for Martian addresses is to solve the abundance of IP addresses around, causing a situation that many houses and offices share the same IP, the same fake IP. Accordingly, Google would never know how to route a reply to us because he doesn't know where we are at. This is solved by the NOT algorithm that we'll display shortly. Those IP addresses are stored in the registry of Windows and in files in Unix. For example, in this hive called local machine, stating the IP address and its subnet mask, a term that we will be getting familiar with shortly. Other information stored in the registry include, for example, default gateway, the router that we leave the local area network when we have a message externally, the default ETL, usually 128 with Windows and 64 with Linux, specifying the number of jumps that are maximum allowed within the web to prevent a situation where a message is going forward endlessly, etc. The original scheme was called class-based addressing. It was good when we had very few machines around and very few IP addresses to share. Let's see an example. If we had a house with 3 computers, we would choose class C, having a maximum of 256 computers with 2 million households. This would be defined by sharing 3 octets and differing on the 4th one. For example, an address like 200, 100, 110, 200, 100, 120, etc. This is very nice, but we don't need 256 computers at our house, and we definitely have more than 2 million households. Those that are bigger offices might want more computers, for example, 30,000 up to 65,000 computers, bounded by sharing of 2 left modes and having no more than 256 to the power of 2 computers in each. Accordingly, only 16,000 networks are possible with this scheme. This might be good for a small office with, let's say, 300 computers, but not necessarily good for Coca-Cola, having many more. Accordingly, Coca-Cola might have asked for an A-type class, sharing almost 16 million computers. However, by doing so and sharing only the left side octet, opening place for so many millions of computers within the same network, it bounded the number of such companies to only 126 by this octet. The idea that this is 126 and not 255 is because the router wanted to make a fast decision which class is that network by looking only on the most significant bit, meaning 0 here, 1 here, and 0 and 1 and 1. To solve all those challenges, scientists have decided that we might use DNE. And this DNE might break the need for smaller offices and households. But of course, this is really not as beneficial as possible and not giving a reply or resolution to classes A and B. The Martian addresses were much better approach, allowing the duplicate of addresses across houses with the NOT scheme. The NOT scheme given by the router allowed the router to represent himself to the destination address in such approach. When a computer wanted to send a message to, for example, Google, and it had an IP address which is not known externally, the router itself would take on the responsibility to convey that message to Google while representing himself instead of the original IP address. Serving that to Google, Google would know how to reply to this router because the router's IP is real. It's not a NAT-based or a Martian-based address. It's a real address given by the ISP. When this reply arrives, this router would use its internal tables to know where to route this reply forward. Accordingly, capturing with an IP and a port specification, the message could go out of a household premise to Google and back, even though there are Martian addresses. However, this was only part of the solution. Over time, class-based addressing is not sufficient. We needed a new scheme called classless addressing.